Hello friends, welcome to our channel. In this session we are going to see depletion load inverter. This is the circuit diagram of depletion load inverter. Before going to this, let us see a resistor load inverter. Here in this resistor load inverter we have enhancement MOSFET as a driver and a resistance, that is the load over here. This is the overall circuit diagram of resistor load inverter. It consists of some disadvantages like much big value of resistors cannot be manufactured on silicon chip as it requires larger area, and also increasing the resistance value we should consider the factor like time constant, delay, etc. So therefore we move towards depletion load inverter because the MOSFETs are easy to manufacture on silicon chip. Here we have an enhancement MOSFET which is a driver and depletion MOSFET which is the load over here, and this is the circuit diagram of depletion load inverter. First we'll see the VTC curve of depletion load inverter. In this, when the input is low, output is high, and when the input is high, output is low. So when the input is VIL, output is somewhat less than VDD, and when the input is VIH, output is VOL. That is, it is not exactly 0, but it is somewhat closer to 0. So this is the VTC curve which we are going to see through the simulation. First let us see the calculation of it. Okay, so these are the specification. That is VD equals to 5 volt, VT naught is equals to 1 volt, VT naught of load is 3 volt, phi F is minus 0.3, gamma is 0.4, W by L of driver is 2, W by L of load is 1 by 3, K dash N of driver and K dash load is equals to 25 microampere per volt. On the basis of this, let us calculate the values. That is VOH, which is when input is low, output is high, that is equals to VDD, so it is 5 volt. VOL, that is VOH minus VT naught driver minus square root of VOH minus VT naught square minus K load by K driver mod of VT load VOL square. Putting the values in this equation, we'll get VOL. How to remove K load, that is K dash and driver into W by L of load. So putting this in, we'll get 8.3 into 10 raised to minus 6. Similarly doing it for K driver, that is K dash and driver W by L of driver. So putting that, we'll get 5 into 10 raised to minus 5. On the basis of this, calculate VOL, that is 0.192 volt. Now the third critical level, that is VIL. So this is the equation of VIL, that is VT naught plus K load upon K driver into V out minus VDD plus mod of VT load of driver. Now for this, VT load of V out is unknown for us. So first we'll remove it. So that is VT load of V out is equals to VT load plus gamma under root mod of 2 phi F plus V out minus under root mod of 2 phi F. Now putting in this equation, we'll get minus 2.36 volt. Now putting all the values in VIL, we'll get a equation, that is VIL is equals to 0.16 V out plus 0.56. Now equating this VIL in terms of V out, we'll get 5.8 VIL minus 3.35. Now when the input voltage is VIL, driver operating saturation and the load operating linear. So therefore we'll write I driver is equals to I load, that is K driver by 2 into V in minus VT square is equals to K load by 2 into, in bracket, 2 mod of VT load of V out into VDD minus V out minus VDD minus V out bracket square. Putting all the values we have got in specification and also in the upper section, putting these values, will get a quadratic equation, that is 1.16 V out square minus 6.15 V out plus 2.55 is equals to 0. Now taking the V out by this expression, we'll get two values of V out. So that is 4.82 and we'll also get the other value, but it is less than 4.82, so therefore I have ignored it and I have taken only 4.82 over here. Putting this 4.82, that is V out, in VIL equation, will get 1.36 volt. Now similarly doing it for VIL, VIL is equals to VT naught plus 2 V out plus K load by K driver mod of VT load of V out, D by dV out of VT load. So here D by dV out is unknown, and as well as mod of VT load of V out is unknown for us. So therefore we'll calculate first D by dV out of VT load. It is given by this formula. Put inside it. Here for V out we have to take VOL, because it is VIH. When input is VIH, output is VOL, as I earlier said it. Put it like that and you'll get a value over here. Similarly calculate VT load. You'll again get a value. Put all the values in the VIH equation so that you will get 1.10 plus 2 V out. Arrange this VIH equation in terms of V out, will get VIH minus 0.55. So when V in is VIH, then V out is approximately VOL. Hence driver transistor operates in linear region and load transistor operates in saturation region. Hence we write ID driver is equals to ID load. Now again putting the linear equations, equating both equation of linear and saturation, and putting all the values, will get equation that is 0.75 VIH square minus 1.55 VIH minus 0.65. Calculating it for VIH by this expression, will get VIH is 2.42 or minus 0.66. We'll ignore here minus 0.66 because our V is not negative. So therefore we'll take 2.42, equating it in the equation of V out, so we'll get 0.66 volt. Now these are voltage levels which we have calculated until now. Now on the basis of this we'll calculate noise margin, which is given by the formula. Low noise margin is equals to VIL minus VOL, so we'll get it like 1.16. High noise margin, that is VOH minus VIH, will get it 2.58. Now on the basis of this, let us do the simulation. So this is the NI Multisim software. In this we'll gather the components. That is, first you have to go in transistor over here, transistor virtual, and then in this select MOS N, which would be our driver, and here select MOS N 4T depletion, which would be our load. Going to the source, power sources, DC power, required DC powers. Then we'll go to ground. Connecting all this. So hence you will connect this circuit in this manner. I have connected it first. So this is a circuit which I have connected over here. In this circuit, we have taken a voltage probe over here that we can get from place probe and we can get the voltage probe over here. So I've joined the voltage probe over here. Now we have to change the parameters of the depletion as well as EMOS. So first changing the depletion MOSFET parameters. I have already changed it. We have to go in edit module and then threshold voltage. Now we know the threshold voltage of depletion was -3 volt. So I have written over here. You should just double tap over here, write the value and enter. So it is -3 over here. Similarly, Kp, that is transconductance parameters, is 25 microampere. So I have written it over here. Now omega by L, that is W by L, width and length. So I have taken over here 1/3 is my W by L ratio, W by L of driver. So I have taken here 1/3, 1 micro by 3. It's 1/3 only. Okay. Then when you have changes, when you change this parameter, I'll do it for you. (3e-6 micro). Then here you can select change component and you can do OK. Similarly, you have to do for driver transistor. You have to change the W by L of driver. Through this, threshold voltage is 1 volt. Transconductance parameters is 25 micro. And W by L again it is 2. So therefore I have arranged it like W is 4 and L is 2. So it will become W by L of driver is 2. Then again select on change component and you will get the parameters. Now for running this simulations, or to simulate this, go on simulate, analyze and simulate, go in DC sweep, take V in over here because we have to see in the terms of V in, output in terms of input. Okay, and value is 5 volt, which is my VDD, and increment I want to see 0.1 volt. Check whether the output has come over here. It is V out, and run the circuit. You will get the curve like this. Now if you will check with the help of cursor, I'll use cursor first. Now when my input look over here, when my input is 1.36 volt, output is 4.8. So I'll do it for you. You can see over here, when my input is 1.36 volt, output is 4.8 volt. Okay. Now similarly, if we'll take, when my input is 2.42 volt, output is 0.66 volt. (2.42 volt), output is 0.62 volt. Okay. Getting it? When my input is 2.42 volt, output is, here it is 600 milli. So you can transfer it over, you can translate it. So it is 0.6 volt over here. Okay. So this is the critical voltage level which we have compared through simulation as well as through calculating the values. So thank you friends. Depletion, we have advantage of depletion, so let us discuss it. Depletion load inverters have good noise margin. VTC curve of depletion load inverter is very close to the ideal curve inverter. So, and manufacturing of MOSFET is somewhat easier than resistor, hence we use the depletion mode inverter. Thank you friends. See you in the next video.